Swayam Prabha. Digital India. Educated India.
Hello, welcome to the class of high performance computing for scientists and engineers, and we are discussing OpenMP programming through this module. This is the module 2. While discussing OpenMP programming, we have mainly looked into different syntax and semantics related with OpenMP, and also looked into memory management issues and task scheduling issues using OpenMP. And now we'll take a step forward and try to see how in scientific computing applications we can efficiently use OpenMP. And as we have discussed earlier, we'll also see later that many of the scientific computing applications depend on matrix algebra, looking into matrices, transforming matrices, rotating matrices, and very importantly solving matrix equations. So the focus of this lecture will be applying OpenMP for parallelizing matrix solutions or matrix multiplications, matrix product operations, and looking into the efficiency while doing so. So what we'll discuss in this class is one important issue will be pitfalls in the performance of OpenMP programs, because when we write OpenMP programs, the main goal behind that is we want fast computing. We want efficient solution. If there are certain issues for which performance of the program can degrade, we need to be aware of that so that our program efficiency increases. And then we will see how we can do matrix calculations. While saying matrix calculations, we will focus on 3 different type of matrix related calculations here, or linear algebra calculations here. One is vector vector dot product, matrix vector product where the solution is a matrix, and this matrix vector product we will again discuss that this is one of the very important applications in many scientific computing tasks, that we need to do matrix vector products, especially when we are solving matrix equations using iterative methods. Matrix vector products are unavoidable, and these are computationally complex problems also. And we will see a further computationally complex problem, which is matrix multiplication, and we will see how we can efficiently implement the algorithms. So it is not only the OpenMP implementation, but we will also see from the serial computing point of view what is an efficient algorithm to handle matrix multiplication programs. We must understand that we are using OpenMP, we are using parallelization, we will later see MPI and CUDA to get fast solutions. But if our main algorithm, if the stem of the algorithm is not efficient enough, we will not be able to utilize all the high performance computing infrastructure efficiently. So it is also important that we look into different other perspectives of the program, like are we handling the cache correctly, are we storing the matrix correctly, issues like that. So we will go through these particular issues also in this class. And I must mention that as we discussed OpenMP programs, also I will show some demonstration codes to present the case where certain methodology has to be adapted to parallelize the program or to augment the efficiency of the program. And these demonstration codes are, I must acknowledge that they are developed by Mr. Nandan Sarkar, a research scholar in Mechanical Engineering Department, IIT Kharagpur. So the codes I will see, most of them are developed by Mr. Sarkar, and also later we will start discussing about MPI. He has contributed a lot in terms of code development for this course. Well, so what are the issues for which OpenMP performance can degrade? Some of these we have already discussed, and some of this we will discuss. One is that there is a serial, always there is a serial fraction of the program. If you remember Amdahl's law, any program cannot be completely parallelized, so there will be certain serial part of the program. So when this serial part of the program will be executed, the other processors are sitting idle. I mean, that you cannot avoid that, there is a serial part of the program. But in case if we try to parallelize this part also, or if we deploy multiple processors or multiple threads to repeat the serial job, there will be no benefit out of that, but we will probably little overdo it, because when we say there is one particular part of the program which has to be done serially, say reading a file, this has to be done serially. So if I ask all the processors to do that, that might add overheads, or that might add serial computing time also. Rather, we will identify one processor and ask it to do this part. So while parallelizing a job, we have to be quite cautious about the serial part of the program and do the right synchronization, so that only a designated processor works on that. So this can, if this has not been handled correctly, this can degrade the parallel performance. And also we need to look into the algorithm and see that the serial part of the program is not large enough. If a program has mostly serial part and a very small parallel component, running it in a parallelized mode will probably not help, because parallel overheads is going to kill other benefits. So we have to be cautious about that. We will discuss some of these issues also in subsequent slides. Latency due to parallel clauses. So when we call a parallel clause, there is latency. There is latency in the sense, if we have not done the proper load balancing, some of the processors will be done with their work, some will be waiting, so there will be latency for them. Who are still working, there will be latency for the processors who have finished their job but working for the other processors. There will be some other parallel overheads also in terms of distributing the job, in terms of synchronization, etc. So this is another part which can degrade the performance. Load imbalance, this also can contribute to latency. This is of course an important issue. False sharing, we have looked into that though two processors are working in two different data addresses of the two different data locations of the same memory address of the same array, but if they are sufficiently close, then they are probably shared in both the processors cache, and therefore the cache coherency protocols are working over them, which gives a sense of false sharing, and the performance degrades. We have looked into it when looking into the sign function calculation, pi calculation in previous lecture. And for that you need to use padding or critical constructs, etc. The other can be contention while updating same memory location, and this is, we will show you an example. This can be very bad if multiple processors are working together and they are trying to update one particular memory location, then garbage values may come out, because one has updated, other has not taken care of that update and further overwritten of that. So this is another issue where performance can come down, because the processors are fighting together to write on the same memory space, whereas one processor can overwrite another's write and you can get a garbage result or meaning result without meaning. So in this particular case, when multiple processors are trying to write to the same memory location, we know that reduction type of operations or atomic operations are helpful. So these two clauses issues we have already discussed, that both false sharing and contention can be avoided using critical or atomic constructs, using reduction clauses, etc. We will rather focus this part of the discussion in understanding this part, that what to do when a part of the program is serialized, or what to do when there are certain latency due to parallel clauses, etc. So avoiding, one issue is avoiding latency due to unnecessary parallelization. For example, I have a program which is mostly serial, but there is some small parallel component, or I have a program which is a small program, I mean, whose computational cost is small. So if we want to divide it across multiple processes, then the distribution and synchronization overhead will be such high that the benefit will not be much. So, that whenever we are doing writing a parallel clause, it is adding some overhead. So, if we are unnecessarily parallelizing a job, say I have to operate over 5 numbers and I ask 5 processors just A plus B type of operations to take care of them. So, this distribution synchronization, these overheads will be such high that because each processor is just crunching one number, this benefit will be overshadowed by the parallel overheads. So, unnecessary parallelism may reduce the performance. We need to see whether it is necessary to parallelize the program, and when it will be necessary to parallelize the program. If not, then we will serialize we will run the serial program. When will it be necessary to parallel program? When the number of jobs are large. In case I have a very small number of jobs, say I am doing some operation for 1700 numbers. I will show you some examples in after few slides only, that this operation like A is summation of 3 numbers. Any processor for a small number of iterations, any processor can do it very fast. So, if we try to divide across multiple processors, then it will take large amount of time. So, if say we are doing something here, that we are using a clause, if the number n, if the number of iterations is greater than 1700, this 1700 is kind of arbitrarily chosen, but it tells you that the number should be large enough, and also when each processor is reading, it's not overflow the cache of the processor. There should not be many cache hits or cache misses. We'll again, as I told you, will see that part. But say if the number n is less than 1700, then this parallel loop will not be executed. Then this job will be executed as a serial process. If the number is more than 1700, only then the multiple threads will be launched and different threads will take part of different iterations. And this is taken from Hagar-Williams book. Some example addition of 3 numbers, 3 arrays is done, and we can see the serial performance. The serial performance, as the number of as increases, serial performance initially increases because it can utilize the entire cache line, and then around 1000 serial performance drastically drops. And then because the number of iterations are large, it takes a large amount of time, then it keeps on, the serial performance keeps falling. But in case we do that up to 1700, where serial performance is good, we will run it in serialized mode. After 1700, then it will go and 4 threads will be launched, will probably get the best performance, because when the number is substantially small, it is running as a serial program. But now one can tell that still why there is little difference in performance, because we are using an if loop here. If it is a serial program, if these 2 lines are really commented out, if it is a serial program, then this if loop would not have been there and there would have been more calculations. Then there are some small issues, let us not focus on that, but the idea is that if we run this program throughout in 4 threads, right, the 4 thread execution, it gives much smaller performance at number of n less than 1. The distribution, synchronization, thread forking, thread destruction, etc. takes substantial amount of time, adds overhead. So, the performance is not right. So, here the part up to which running in multiple threads is not beneficial, we run it as serially. And when running multiple threads are not beneficial, when the task is small. So, if the given job is small, it is more judicious to run it serially. If the given job is large, then we can launch multiple threads. If the computational task is small, you either run parallelly or use small number of threads. Each parallel region, and then another part is latency due to synchronization issue. Each parallel region is some way synchronized. That means once threads are launched, they will finish their work, and then there is a barrier. Each thread will wait till others have finished till that part of the job, and then threads will be destructed and the next parallel region will start, or next part of the codes will follow. So each parallel region has an implicit barrier where each thread has to wait for others to finish their work, and this adds a synchronization overhead. That means this is adding a latency, which is an overhead to the threads. In case I have a program where output of one parallel region is not important for the next parallel region, I can use a no wait clause which will break this synchronization. Threads do not have to wait till the end of that particular parallel region and go to the next part of the work, and that will consequently reduce the overhead. So say this is an example which is without no wait clause, a simple parallel regime. Initially the parallel regime is launched, so each thread updates their private memory B. A is a shared memory variable, and then each thread, I'm sorry, this might be shared memory also. Each threads update the variable B as given to them. Now there is a, so they call a function, so let's call a function and update some variable. And now in the for regime there is a loop in which some variable C is updated, and then this parallel regime, this for loop ends, then a variable D is updated by the threads, and then this parallel region ends. At this point only all the threads are free and they can work on the part Z. If we look into the execution pattern, say for thread 0, because this is outside the parallel region, thread 0 is only active here, A is updated at thread 0. Then the part B is done by all the threads. Then for the part C, this is an iteration, and say 4 threads are active over 10 number of iterations. So few threads work for 3 iterations, few threads work for 2 iterations. But this is a particular parallel construct. So unless this construct is over, unless this parallel region is over, the other threads are waiting, these 2 threads are waiting till they have finished their job, till the threads which have more work, they have finished their job. And then once they finishes, everybody does the part D, and then again all the threads are distracted and part Z is done. Now we assume a case where the output of this function C doesn't is not required by the functions D and Z. What we can do, instead of allowing this wait time by these 2 threads, we can use a no wait clause here. That means once these 2 threads jobs are done, they can directly pick up the task D. So they are not, their thread 2 and thread 3 is not waiting for thread 0 and thread 1, rather they are finishing their own job. We are destructing the barrier there, we are destroying the barrier there. So this is done to reduce the synchronization overhead, and then if we can if we can efficiently design the algorithm, in next part probably will give more tasks to say thread 2 and thread 3, something like that. These things can be planned. Or we can put another for loop where more tasks are given to thread 2 and thread 3, so they can pick up, and we can save in terms of time. This is taken from Aalto University's high performance computing web page, these figures. And sometimes when a variable is updated using critical, this no wait clause can help. Why? Critical means this is inherently a sequential part. Each thread is updating the executing that part of the job, and other threads are waiting for that. In case we use a no wait and make them free, they can go into the critical part, and these 2 threads are still working, but by the time they have finished writing the critical variable, they will be finished and they will take care of the job. So you can save more in terms of time. What happened? Avoiding load imbalances. If the number of threads are comparable to number of tasks, task per thread is small. We are doing a load balancing, we are trying to give almost even number of tasks to each threads. But if say I have 10 tasks and 8 threads, So each thread is getting one task and there will be two tasks, so two of the threads will get two. So the difference, the amount of task given to each thread is small, and the wait time for each thread, because the others have not finished their job, some threads have two tasks, is also comparable to that, which is not good. In case you have less number of tasks compared to the number of threads, I mean you do not have large number of tasks compared to the number of threads, task per thread is small, and sometimes it is comparable to the imbalance between the threads. Therefore, the latency and overhead will be high in as compared with the computational time. A thread is doing 1 unit of task, it is waiting for another unit, which is bad. But in case I have 8 threads and 731 tasks, then each thread is giving is getting 91 tasks or 92 tasks. So, the thread which has less tasks, they got 91 tasks and waiting for one task by some of the other threads. The waiting time comparable, like the compared waiting time is small, the overheads are small in that particular cases. So, trivial load balancing, we will try to avoid that number of threads are comparable to number of tasks, we will try to assign number of threads which is much less than the number of tasks. Avoid dynamic guided load balancing unless necessary. Again, for small tasks, for threads, if we use dynamic or guided, if we use static load balancing is once done and fixed. You do not need any complicated algorithm to do load balancing. But if you are using dynamic and or guided load balancing, there is some algorithm, there is the compiler has to do something else to do the load balancing, and that will add to overhead. In case we have less number of tasks, then this overhead can be large. So, if it is not absolutely necessary, do not do dynamic or guided load balancing. In certain cases, for handling large jobs, they can be very helpful, but in general, if you are working with small or medium complex problems, do not use these load balancing techniques. Use collapse clause for load balancing over multiple threads. This can help in avoiding trivial load balancing. This is an important aspect. We will see some of these issues later on matrix calculating. In case we are using a parallel do loop over multiple loops, there are multiple loops, and we are not doing nested parallelism, we are doing simple parallelism with one parallel do loop. So, what happens when these nested loops are parallelized? OpenMP by default takes the first outer loop and parallelize the iterations in the first outer loop. The internal loops are same for each of the threads. So, threads are assigned only to the first iteration loop, only this loop is threaded here. Now, here the number 1 to m can be not a very high number, can be small, say 1 to m is 10, 1 to n is also 10. So, therefore, and all n is 10 and m is 10, therefore, there will be total 10 to the power 4 iterations. However, if we try to parallelize it, each thread will get a fixed load balancing on the outer loops, which can give less number of tasks to each thread. The tasks are heavy, however, the imbalance can be more because the outer loop tasks are only threaded, therefore, there can be more imbalance there. So, one idea can be imbalance is not more, rather imbalance is large comparable to the given number of tasks. That if you use a collapse of level 2, what will happen? That first two outer loops will be collapsed and both of them will be threaded. So, threads will not be launched not only in the outermost loop, but also the inner loop will be threaded. That means one thread, it will take say first 10 first 5 of the outer loops. Inside each of the outer loop, there will be threads which will take care of say first set of the inner loops. So, collapse can do threading over first two outer loops, and this can sometimes give you less overhead because it can avoid the trivial load imbalance problems. Now, we come to matrix computing applications. That these are the few things. Apart from that, we know about fault sharing and write invalid or trying to write in the same memory parallel write issues, contention while writing to the same memory location issues. But apart from that, this load imbalance problems, especially trivial load imbalance and the serial part of the program and latency due to some threads waiting for some other threads who have not finished their work can degrade the performance. Now we have to be cautious and utilize OpenMP constructs efficiently and smartly, so that we can avoid the overheads there, we can get better performance out of the program. Now we come to the linear algebra applications, and one of the basic application is a vector dot product. Now if you can understand that if we do a vector dot products, so what is that each element of the vector, one vector is multiplied with corresponding element of other vector and they are summed up and finally we get the sum. So in case we have a vector of size order 100, dimension 100, then there are 100 into 100 and then multiplication of 100 times and addition of 100 times, 200 operations. So usually the number of operations in vector dot product is not large. Therefore, in some cases where you are dealing with vectors which are of the order of millions or 100 millions or billions, apart from those cases, you really do not like to parallelize the vector dot product program, simply due to the fact that it is not computationally much complex. Sequentially it can be handled quite well, and we will see some of the examples. But in case you have a vector of very large dimension, you may like to parallelize this. So we will look into the sequential program, what is happening in the sequential program. See here the dimension is given 1000, so two vectors of size 1000, dimension 1000 are declared and they are initialized to be 1, and then what we do, that the dot product is each of the vector element. A is the address, a plus I gives is the address of the beginning of the vector, of the start of the vector, a plus I gives different ith element of the vector, and they are added and written to the vector variable c. So in a 48 core 2.2 gigahertz Xeon processor with 192 gig RAM, it took 10 to the power minus 5 seconds for n is equal to 1000. It is a serial computational time, the single processor. So, you are not using 48 cores, we are only using 1 core here when we execute this program, because this is not an OpenMP program. I have added OMP.h only for finding out the time. We are using OpenMP calls, OpenMP functions, but it is not an OpenMP program. We are neither using 192 gig RAM because it is a very small program. Well, so if we have to parallelize it, what we will do? We will parallelize this for loop. Forget this is initialization, but this for loop is the dot product calculation. So this is iterating over I is equal to 0 to I is equal to the dimension of the vector, and in case we want to parallelize it, we will include a OMP parallel for construct here, and that will launch multiple threads and parallelize. This loop can be parallelized. This also can be parallelized, but I am not looking here because this is initializing. So now if we try to parallelize it, what we will do? We will write pragma OMP parallel. We will look into the dot product part. Pragma OMP parallel for private variable is I here, and all other variables ndim, ca all are shared. Default is shared, private I, and parallelize it. And is our parallelization right? For that, what I do, because these vectors have valued 1, so their dot product is basically 1 into 1 plus 1 into 1, so on. So it's if the number of elements are n, that value of the dot product is n. We will check whether the difference between the dot product calculated by the program in a parallelized manner and the actual dot product C, actual value, which is n dimension or dimension of the vector, are same. What is the error? We will write that. Well, so when we parallelize it and serial computational time is 10 to the power minus 5 seconds, this is very interesting. If it go in 2 threads, the computing time is 10 to the power minus 4, the 4th thread's computing time is 2 into 10 to the power minus 4, 8th thread's computing time is more. So, as we are increasing time threads, then computational time is increasing, and error is huge. I mean, we are getting some garbage value. So, because the error from the actual value should be C val, the error between C val and C is huge, and as we are increasing number of threads, the error is increasing. So, what happened wrong? Well, we try to update the variable C by all the threads concurrently. The same variable location where all the threads are trying to write. So, all threads are trying to update the same variable simultaneously, therefore, contention due to writing same shared variable C happened, and it ended up in writing garbage values. Well, so what we can do? We will not try to update it simultaneously, we will put a critical construct here. So, that's exactly what we have done here. Here we put, so this is parallel, the for loop we have launched it separately, you can do it otherwise also, and then when we are updating the variable C, we put pragma OpenMP critical. So, each of the thread can execute this particular operation serially. So, what happens, the error reduced to 0, but the parallel time is, earlier the parallel time was 10 to the power minus 4, and now the parallel time for 2 threads is 3 into 10 to the power minus 4. Parallel time increased, the computing time increased, as we are increasing number of threads, the computing time is increasing. And why is it so? Because again critical construct tells each of the threads to wait till others can write it. So, the time is increasing. However, error is reduced because the contention has been reduced, no garbage values due to synchronized update threads at C, but overheads due to critical construct. Well, the other way also, because the computation is less compared to the overhead, the time is increasing. I told you that this, I mean, for 100 by 100, for 100 size vector, computation will be less. So, overheads can really kill the problem. Well, the other way out will be, because we are updating the variable C and its addition, we just add a reduction clause. Reductions are very optimized clauses. So, what happens when we run reduction clause? Computing time reduced, but it's again it's not comparable to the serial computational time, it is more than serial computational time. Error is 0, which is fine. So, still computation time is more than the serial time in parallel, because the matrix is a the vector is a very small vector, the computational task given to it is quite small. But if we increase the vector to be 1 million, and then serial computational time is 7 into 10 to the power minus 3, and we can see with the reduction clause, with increasing number of threads, computing time is reducing. So, because the task is more here, parallel performance is better. So, if for a small task, that proves our initial proposition, if the task is small, do not parallelize it. If the task is large, because we were doing it for 1 million size vector, then there is some benefit of parallelizing it. Well, program performance improves with higher values of n. Now, we come to more important issue, that is matrix vector product. Matrix vector products are extremely important in linear algebra calculations. In matrix solvers, iterative solvers, we know about it. In preconditioning, in many applications we use matrix vector products several times. In matrix rotations, matrix transformations, these are the domain of scientific computing is infested with matrix vector products. So, these are unavoidable, and if you look into matrix vector products, a product between a matrix and vector gives us a vector. Each element of the vector comes as summation of all the items elements of the row of that matrix multiplied by the corresponding elements of the vector. So, if there are for each row, if this is n by n size matrix, an n dimensional vector, each row there are n operations, if there are n rows, there are total n square operations. So, number of operations are large, therefore, parallelization benefits will be good here for large values of n. So, we have written a matrix vector product here. It initializes the matrix with all elements 1, vector all elements 1, and then multiplies them and writes it here, and the computational time is 7 into 10 to the power minus 3, 7.5 into 10 to the power minus 3. Now, if we have to parallelize it, the parallelization will be very simple. You only have to write a parallel construct before the matrix vector product out loop, and which of the iteration loops it will parallelize, it will take the outer iteration loop and parallelize it. And also you do not need to worry about false sharing, or even you do not need to worry about contention while writing it, because each of the thread will update a different element in the product row. There will be some false sharings which is okay. I mean, only at the, because it's always you are doing large number of computations, only at the ends of the iterations of each thread there might be some sharing, might not be also. This is not severe here. Well, so threads are launched only over the outer loop, and if we see the serial computing time, which is 7.5 into 10 to the power minus 3, parallel computing time improves as we are increasing the number of processors, the computing time reduces. As the number of operation is of the order of n square, therefore the total task number of operations are more, total tasks are more, therefore we get better performance here. If we increase the size from 1000 to something more, we will get even enhanced performance, and there is no contention because each thread is writing to a unique memory location, they are not trying to update the same memory value. Now we look into a Fortran program. So what was in C program, that each row of the matrix each element of the matrix row is multiplied with the corresponding vector element of the vector. Now if we do same, that each row of the matrix is multiplied by the corresponding vector element, we will see computing time for this matrix is larger, 10 to the power 5 is 0.92 second. Instead of doing the row wise multiplication, if we do it column wise, that each columns all row elements will be multiplied by the column, and because this matrix we are defining everything 1, there is a symmetric matrix, this will be equivalent here. If not symmetric, then instead of B we have to store it as B transpose. We will see that time is much small, 50% of that. And why is it? And this, there comes certain cache issues. When we are accessing the matrix column wise, in Fortran the matrix is stored in a column wise manner. We are utilizing the cache more efficiently, where there are less cache misses. When you are accessing it row wise, as the matrix is stored column wise, every operation is giving you a cache miss. Therefore, the computing time is almost double for row wise multiplication. If we focus it a little more, that in a matrix is a 2-dimensional entity, here 2D matrix, which it, or it is a 2D array, but when it is stored, it is stored only by the address and the size. So in C, the compiler stores the matrix as the first location and then moves as a, and then maps everything as a contiguous array. So first row is stored, then second row is stored, then third row is stored, so on. It is stored like a contiguous line. And this is called a row measure order. In Fortran it is rather stored in column measure order, that first column is stored, second column is stored, third column is stored, so on. So when we access the first elements of the first row, this element, this element, these elements are accessed, they might be in the same cache. But in Fortran, when we are trying to access this and this and this, if this is a large matrix, they are not in the cache line. The cache line contains the columns only. Therefore, as Fortran stores the matrix in the column wise, in calculation of this, there will be cache miss every time for a large matrix, because this, if this is the cache line, A12 doesn't, A1 cache starts from A11, A21, A31, AN1 up to the cache. A12 is never on the cache line. So every time there is a cache miss. Therefore, while looking into Fortran, we have to look into the column measure order, or we have to go column wise. So by storing the matrix in transpose manner and calculating AJI BJ, instead of A we store AJI A transpose, that will ensure in Fortran that we are going column wise direction, and we are ensuring cache hit every time. Therefore, a huge performance difference can be seen if the matrix is large. If the matrix is small, entire matrix might fit into the cache, if we are just talking about 3 by 3 matrix. But if we are talking about million by million matrix, then the performance issue will be significant. Now, it's for small matrix it will not be substantial, and the columns can fit in cache. Now in C it's stored in row major order. In case we use the try to store it as B transpose and multiply it in C, then there will be problem because the matrix is stored in the row major order. Now there will be a, therefore the parallel performance will also behave safely. If we similarly, if C we have to access as a row major order, we have to access the matrix row wise, parallelize it similarly. In Fortran we have to access the matrix column wise and parallelize it similarly, else there will be degradation of performance. Now we look into matrix multiplication. These are not as abundant as matrix vector multiplication in scientific linear algebra applications. However, there are many cases where you have to do matrix multiplication, and the number of operations are quite high, n cube. If the matrix is of the size n by n, matrix multiplication will take n cube operations, which is huge. If we think of direct solution of matrix equations, we have to use matrix multiplication like Gauss elimination or inverse of matrix, then we need matrix multiplication. The operations are huge. So it is always beneficial to parallelize it. What happens that we pick elements of one row, multiply it with the corresponding elements of the column of the other right multiplier and sum it up and find the product. So always one matrix is accessed in the basic algorithm row wise, another matrix is accessed column wise. So be it C, be it Fortran, it is either row major order or column major order is the storage. So if we try to access row wise and the other one column wise, the other one will always give you a cache miss. And also, so we have to do something for that, I will show you that. And also, while finding out one element in the product matrix, we have to take one line of the right matrix, one line of the left matrix and multiply them and find the product. So number of memory locations are accessed and only one element of the product matrix is obtained. But we can see if we take this line and this row of a matrix, we will get this value. So this is accessed many times, this row is accessed many times for different elements, but reading a row means the taking number of elements from the main memory to cache. So we are doing this exercise several times and not reusing the that part. So there will be memory latency issues because large number of memory locations are accessed for getting one element. Again for getting another element, many of the same memory locations will be accessed and this element will be obtained. Again for getting this element, these memory locations will be accessed and we will get this element, but this and this, they are two different iteration loops, maybe different threads are responsible for that. But essentially the same exercise for fetching the memory is done several times for the same memory location for getting different computing. This is one issue in terms of memory latency. So this is the simple implementation that each element is the Cij product matrix is obtained by multiplication of the row of the matrix A and row of the column of the matrix B, and the time for N300 is 0.2 second, N1000 is 5.27 seconds and 3000 is 379 seconds. So you can see it is almost cubically increasing. Now if we do a cache friendly implementation, this is not cache friendly because this is a C program and A is accessed row wise, which is cache friendly.
B is accessed column wise. So, each value for one particular row element, different columns of B is being accessed. One B is accessed column wise. So, one particular column, different elements of the column is being accessed. So, J is fixed, column ID is fixed, and different elements of the columns are being accessed. They are not in the same cache line. So, this is not a non-cache friendly example. So, what we can do, instead of B, we can take B transpose and multiply it. We can store B as B transpose, or rather we can store the B transpose directly and multiply row of A with row of B transpose. So, we have stored B transpose instead of B and multiplying row of A as row of B transpose. Row of B transpose is column of B. Doing the same calculation but storing it differently, so that both the matrices are now accessed column wise. And you can see the difference in time. For 300 it is 0.21 second. For a large matrix it is almost 1/3, more than 1/3 of time has been saved while doing a column wise access. It saves more time for larger matrices. While obtaining, so this is one part that we have to access. In C we have to access both the matrices column wise. In Fortran we have to access, in C we have to access both the matrices row wise. In Fortran we have to access both the matrices column wise, and even we parallelize or not parallelize it, this performance difference will be there. Even with parallelization we will get better performance if we do cache friendly access. The other part what I was telling is that for obtaining one element in the product matrix, we fetch entire row and column respectively from the multiplier matrix. So, each element requires one row reading, one column reading. One value of the register is used for the cache lines comprising one row of A and one column of B. Let us see that we are calling it in a cache friendly manner. Instead of B we are calling B transpose. The rows of A and B are repeatedly loaded into cache for calculation of other elements. If we can unroll the loop, if cache size is less than row size, there will be cache misses for during these calculations. Well, if we can unloop the loop, that row column combinations, few rows and few columns are read, and all the calculations using these row columns are done once. So, that means instead of only calculating one element in the loop of the C matrix, we will calculate multiple elements of the C matrix, and we will do that Cij, Ci plus 1j, Cij plus 1, Ci plus 1, j plus 1. So, what are we doing here? We are reading ith row of A, bth column of j, I plus 1th row of A and B plus 1th j plus 1th row of k, right. So, we are reading ith row, I plus 1th row, jth row, j plus 1th row. We are reading 2 rows of A, 2 columns of B, and doing 4 calculations of C elements. Here we are reading 1 row of A, 1 row of B, and only doing 1 calculation. Here we are total reading 2 row, 2 columns, 4 cache readings we are doing, and doing 1 calculation, and this 4 calculations. So, more calculations are done as compared to the memory access, and we can see the performance that when we run this code without simple row access multiplication time, without simple row access, that we are accessing the matrices row wise, that's what we are doing for both the cases. It was 0.21 second. Now, once we unroll the loop, for we are doing it for 4 elements in the C matrix, the time is less, 0.18 second. For larger matrix, row access time, simple calculation time using row access pattern is 119 seconds. For loop unrolling it is 88 seconds. And we can see there is another idea of cache blocking, that instead of reading 1 row 1 column and 4 row 4 column and calculating only for 4 elements, read a block of rows, read a block of columns, and do all the calculations pertaining to that, and it helps to reuse the same data. Instead of loading individual row column, load a number of blocks of rows and blocks of columns, and multiply for a block of the product matrix. You can, instead of loading the full row block, full column block, you can load part of row block, part of column block, depends on the cache size. So, fill the cache with contiguous memory, and you have to map the memories contiguously so that you can do it correctly, and then calculate one part of the product matrix. This if you can map the, you have to map the memory contiguously. If all the memory fits in the cache correctly, the blocks size of the block fits the cache correctly, then you can get much faster performance. But now with simple row access multiplication, which is accessing both column both A and B row wise. So, instead of B we are doing with B transpose, and here we are doing row access, along with that we are doing loop unrolling, and we can see the performance with parallelization. Again parallelization will be only in the outer loop, it will be simple as matrix vector product. So, the computing time, which was for one thread 119 second, for 32 threads it comes to 7 seconds. For loop unrolled it comes down to 5 seconds. So, parallel performance is also better when you do this loop unrolling part, and parallelization is very simple. Here you only have to put a parallel for pragma, mentioning the right private variables and the shared variables, and this is one way of using the registers efficiently and using cache friendly access, getting efficient solution, efficient implementation of matrix multiplication. So, these are few references which we have used for this slides, this lecture. We looked into performance improvement scopes of OpenMP program by avoiding trivial load balancing and avoiding synchronization overheads, etc. We looked into how efficiently matrix operations can be done, especially looking into the cache friendly access pattern, row wise access for C matrix, column wise C programs, column wise access in Fortran programs. These are cache friendly access patterns, and also loop unrolling helps in matrix multiplication, and looked into OpenMP parallelization of matrix operations. Basically, for dot product OpenMP parallelization is little critical, you must not do it unless the vector is large. But for matrix vector and matrix product, parallelization is straightforward. Your main algorithm must be cache friendly and efficient enough. Parallelization is only by calling pragma parallel for loop. This for loop will be active as it will launch threads only over the outer iterations, and it gives good results. So, these are some scientific computing related applications we have discussed here, and now we will from the next class we will look into the MPI based program and go to the third module of this course. Thanks.